Right, so welcome everyone to this video where we'll be discussing tutorial sheet 8 of physics. This is BMPH 110, physics for first semester, or medical physics rather. And in today's tutorial, we'll be focusing on what we call rotational kinematics, specifically on torque and rotational equilibrium. So I'm sure by now, almost all of you have heard about this word before, torque. We've heard about the word torque, and sometimes it will be called the the turning effect of a force, or sometimes even moment of a force. So torque is just it's what makes things rotate. You can imagine having a pivot, a fixed point there, then you have an object attached to it. The the measure of how much force causes this object to twist or spin around this particular fixed pivot is what we are calling torque. So it can be calculated mathematically. We said torque is equal to force, which is the force that is being applied, multiplied by the perpendicular distance from the pivot, multiplied by perpendicular distance. I'll say distance with a subscript b. So this is how we can calculate torque. So we're going to see how this actually, or this particular torque or moment of a force is actually applied in different scenarios in physics, starting from seesaws. We'll look at how it is also used in muscles when lifting weights, and many other applications. So without wasting much time, let's go straight into question one, which is saying part A man applies a force of 300 Newton at an angle of 60 degrees to the door of figure 5.5. So this is figure 5.5 that we have there, 2 meters from well-oiled hinges. Find the torque on the door, choosing the position of the hinges as the axis of rotation. So the position of the hinges is the axis of rotation. So if you look at this diagram, or I can also draw a free body diagram, but this one is actually simple. So this is a top view of a door. We have this particular door, then we have a hinge here. And this hinge is a fixed point on a door. So which means this is the part that is going to act as a pivot in this particular case. Then we have a force that has been applied here. We have a force that has been applied at that particular point, and it has been applied at an angle theta with the positive x-axis, which is equal to 360 degrees. So we've said the force that we're going to be looking at, or the force that we are concentrating at, is perpendicular to the distance from the pivot. So if we have a force that has been applied at that particular angle, we are going to have a force that is in the y-axis and a force that is in the x-axis. And the force that is perpendicular to the distance from the pivot is this guy that we have in the y-axis. And we're going to resolve this. This is, or the x component is adjacent to the theta, the 60 degrees. So it is going to carry a cosine. So this will be F cos 60 degrees, whilst the y component of this particular force is away from the theta. So, or it is opposite to the theta. So it is going to carry a sine. So we're going to have F sine 60 here. And since this is the force that is perpendicular to the distance from the pivot, that is the force that we're going to use. So we are going to apply the formula for calculating torque about the pivot of the door, which in this case is just a hinge. We're going to say torque represented by the letter tau is equal to distance r multiplied by f sine theta. This is what we're going to use. So r is just basically distance or radius from the pivot itself. So I'll say this will be equal to, we've been given the distance in the diagram. We've been given the distance from the hinge to where the door handle is, or the lever arm of the door. That is 2 meters. That is where the force is acting. So that is going to be our r. So I'll say 2.0 multiplied by the force, which is 300 sine 60 degrees. I plug this into my calculator. I'm getting my torque as equal to 519.6 Newton meter. 506 or 519.6 Newton meter is the torque produced by the applied force about the pivot, which is in this case the hinge. So that is part A of question one. We can go to the next part, which is part B. So part B is saying, suppose a wedge is placed 1.5 meters from the hinges on the other side of the door, what minimum force must be applied in part A? What minimum force must be applied in part A? Won't open the door. I don't know what they're trying to say here. Let me wrap this first. Here, they're just basically asking us to find the minimum force the wedge must apply to prevent the door from opening. So they want us to calculate the minimum force that this wedge must apply for the door not to open if this 300 force has been applied at a distance of 200 meters from that particular, or from not 200, sorry, 2.00 meters from the pivot, which is the hinge here. So what are we going to do? We are going to find now what we say, or we're going to use what we say this door is going to be at equilibrium. If this door is not opening, that means the forces are going to be at equilibrium. And what are we going to say? We're going to say the sum of the clockwise moment should be equal to the sum of the anti-clockwise moment. So we have the force on the which is being applied by the wedge, which is pulling this door on this side, and we have this applied force, which is trying to pull that door from that particular side. So if this door remains at equilibrium like that, that means the forces are at equilibrium, meaning the forces that are acting in this particular direction are equal to the forces that are applying in that particular direction. So what are we going to say? We're going to say, this is part B. I'm going to say in part B, that means the torque, this is the torque by the wedge should be equal to the torque by the applied force. And this is going to be equal to what? We already know the formula for calculating torque. So the torque that is going to be as a result of the hinge that will be applied will be equal to F, which is the magnitude of the force of the hinge multiplied by the distance from the pivot. So we've already been given the distance to say this is 1.5 meters. This will be equal to what? This will be equal to the torque by the applied force. So we've already calculated this, and we've said this is basically equal to 519.6 on the other side. So I'm going to divide both sides by 1.5 because I want to find the force. 1.5 and then even this side by 1.5. So I'll cancel out here. So that means the force by the wedge will be equal to, I plug this into my calculator, 519.6 divided by 1.5. This is going to give me 346.4 newtons. So the force that should be applied by the hinge should be equal to 346.4 newtons, ladies and gentlemen. Okay, so this is the end of our question 1. We can now move on to the next question, which is our question 4, which is saying the leg and cast in figure P4.40 weigh 220 newtons, which means the leg and cast weigh 220 newtons. That is W1. So which means in this diagram that I'm having here, W1 at this point is 220 newtons. Then they're telling us to say determine the weight W2 and the angle alpha so that no force is exerted on the hip joint by the leg plus the cast. Okay, so I've solved this question countless times. It is there in my videos that I've posted here already. It is there on the website. In the previous tutorial sheet, they repeat this question almost each and every semester. They like it a lot. So here we're going to apply the knowledge on equilibrium forces. Because we have all the forces here that are balanced. We have 3 forces that are acting on this particular point that is here, the center. And we have to, and if these forces are balanced, they're asking us to find the weight or the magnitude of the weight W2 and the angle alpha. So what are we going to do? We're going to resolve these forces into their respective X and the Y components. So I have different forces, meaning I'm going to use different colors. So for W2, we're going to notice that it is going to exist in both the X and the Y axis. So in the Y axis, it is going to be at that particular point. Then in the X axis, it is going to be at that particular point. So we can see to say the X component is the one which is adjacent to the alpha, which means it is going to carry a cosine. So this is going to be W2 cos alpha, whilst here we're going to have a sine. This will be W2 sine alpha, since the Y component is opposite of the alpha, the angle that we've been given. So that is resolving W2. We can resolve W1, or rather the other force, which is the 110 Newton force. This is also existing in 2 axes. There is a component in this particular axis and another component also in the vertical axis there. So the X component is the one which is adjacent to the 40 that we've been given here, which means it should automatically carry a cosine. It is going to be 110 cos 40 degrees. Then this is away, or the vertical component is away from the given theta, so it is going to carry a sine of the reference theta. So I'm going to say 110 sine 40 degrees there. Okay, then there's no need of resolving W1 since it's already existing in only one axis, which is the negative vertical axis. So since these forces are at equilibrium, what are we going to do? We are going to express the equilibrium forces in both the horizontal axis and the vertical axis. So in the horizontal axis, if the summation of forces is equal to 0, that means automatically this is equal to that. So this is pointing in the negative direction, so I'll consider it negative. This is pointing in the positive x direction, so I'll consider it positive, which means W2, this is in the x-axis, W2 cos alpha should be equal to 110 cos 40 degrees. So you can tell to say I've taken this one from this other side. It was a negative before. It was this minus that being equal to 0. But I've taken it to the other side such that it has also become positive like that. That is our equation in the x-axis. We can move on to the next equation in the y-axis, or I can simplify it further. I'm going to come up with it. W2 cos alpha being equal to, if I plug in 110 cos 40, 110 cos 40, 110 cos 40, cos 40, I'm getting 84.26. This is equal to 84.26. Okay, that is in the x-axis. Let's look at the equilibrium forces in the vertical axis. Let me change my pen. In the vertical axis, I have this force which is pointing in the negative y direction, and we have these two forces that are pointing in the positive y direction, which means I'm going to have W2 sine alpha plus 110 sine 40. This will be equal to 220, like this. Okay, so I'm having my W2 sine alpha minus 110 sine 40. So, oh, sorry, I'm going to have my W2 sine alpha being equal to 220 minus, it is now going to become a negative. Let me plug in 110 sine 40 into my calculator. 110 sine 40. Sine 40, okay, this is 70.71 minus 70.71. So I'm going to have W2 sine alpha being equal to 220 minus 70.71. This is giving me 149, 149.3, 149.3. Okay, so now we have two expressions. We have an expression in the y-axis and an expression in the x-axis. So what are we going to do? We're going to say this, if you can say this is equation 2, and this is equation 1. So we're now going to divide the equation 1 into equation 2. And what are we going to come up with? We can now go to a blank board and rub this. This is now question 4, or part B of question 4 rather. Why do I keep on saying part B? This is just question 4. So I'm going to say expression or equation 2, which is equal to W2 sine alpha being equal to 149.3 divided by W2 cos alpha, which is equal to 84.26. Okay, this is what we have. W2 and W2 can cancel out. Alpha and alpha can, oh, not alpha, sorry. We can't cancel out the alpha since it's the angle here. Sine divided by cos, this is going to give us tan. So we're going to have tan alpha being equal to 149, or I can just say 149.3 over 84.26, like this. Okay, so I'm trying to find alpha, so I'll say my alpha is equal to the tan inverse of 149.3 over 84.26, like that. That means my alpha is basically equal to, if I plug this into my calculator, I'm getting 60.56. My alpha is equal to 60.56. Now that we've calculated the alpha, we can now find our W2 using the expressions that we had in the previous page. Let me just go back a bit. We have these expressions. So I can use this to calculate the value of our W2. So I'm going to say using equation 1, we have W2 cos alpha being equal to 110 cos 40, like this. So we're going to say W2 will be equal to 110 cos 40. We said this was 84.26 divided by cos alpha, of which alpha is just 60.56. 60.56 degrees. And this is going to give us a value of W2, which will be equal to 171. Let me just grab this. 171.44 newtons. So that is that, ladies and gentlemen. That is the last question, which is question 4. And W2 is actually having a magnitude of 171.44 newtons. Thank you very much for watching. For any queries, kindly contact me. I'll be readily available and respond to you in the shortest possible time. Until next time, stay blessed.